So hey there, this is Debesh, the info security researcher. Welcome to the Learning Times podcast that is engaged in featuring technology and associated humans. Today is a special episode. It is a mini workshop on computational photonics by Professor James B. Cole and Dr. Saswatee Banerjee. The mini workshop on computational photonics will include three parts. Part 1, Computational Photonics, an introduction, that is today, December 6, 2025. The Part 2, Finite Difference Methodologies and Real World Problem Solving, that will be on December 13, 2025, the coming Saturday. And the final Part 3, that episode will contain real time propagation of light in complex media, that is on December 20, 2025. All episode sessions will feature live demos and question and answers. Now, about the guest speakers. Professor James B. Cole, who is now on the screen. Professor James B. Cole likes to teach science by following the historical thought processes that preceded what we now know. He graduated from the University of Maryland, USA, near Washington, D.C., PhD in particle physics. He did a postdoctorate at the NASA Goddard Space Flight Center in the Laboratory for High Energy Astrophysics to compare experiment with theory and learned about modeling, simulation, and algorithm development. By a strange sequence of events, he would up at the University of Tsukuba, Japan, where he taught mathematics applied to optics, photonics, and engineering. He spent more than 25 years total in Japan. He is now a consultant in quantum computing, optics, and photonics in the USA. Now, Dr. Saswatee Banerjee. Saswatee Banerjee is an applied physicist with a passion for writing, speaking, teaching, and popularizing science. She has a successful track record in industrial R&D in optics and photonics to develop innovative devices with unconventional performance. She has published and presented numerous scientific and technical articles to professional journals and international conferences. She is a senior member of Optica, the erstwhile Optical Society of America, and a respected reviewer with many scientific publishers. She is a creative professional specializing in delivering scientific speeches to curious audience through Toastmaster activity and through podcasts to more specialized audiences. So, over to Professor James B. Cole and Dr. Saswatee Banerjee. Hello, James, and hello, Saswatee. A massive welcome to the Learning Times podcast. The platform is all yours. There is no hurry and no time limit. Please, over to James and Saswatee.
Okay, good evening. My name is James Cole, and I'll be speaking first. So I'm going to share my screen with you in a moment. I have to understand, let's see, I have to select a window or screen, yes. And I think up here,
Yes,
yes.
yes, the plus.
Yeah, live, okay. And then I need to get my, so I have to allow everything. And then how do I get my PowerPoint?
Yes, it will come. Okay, just a minute. Yes, where it is. Again, it has gone. Just a minute. It has gone. You do it again. Where is the presentation? It just came. Screen share again. Yes. Yes, this is the file. Any problem? I cannot hear you actually. I cannot hear you. Your microphones are mute. I cannot hear you. Yes, yes, yes. You now make that full presentation.
Right,
Full
so
screen.
now we'll go full. Oh, wait, it will. There we go. Wait. Here. All right, now I think from the beginning. Okay, I think we're fine. All right, now can you hear me?
I can hear you. Yeah, I make the
All right,
presentation in full size, presentation
full
mode.
size. It's full size now. I
Yeah,
believe it's full.
but it is showing that file view.
Oh, that's funny. Here, escape here. Oh, maybe we need to get rid of this. Oh, now our screen is full. Screening is not allowed to. How is this? Can you see the full screen?
No, it is just file view, like the directory view.
Oh, on our machine it is full view. No,
No,
let's see.
you make it a full, but it is showing the directory view.
All right, this is strange.
What you can do. This one is open. Quite. Mhm. Okay. entire
just,
screen.
maybe that's it.
No, that won't happen.
No,
No. Oh,
I'll try it. Just try it.
In the screen share, it shows the window which one you want to. In the
yes.
plus from plus.
Mm. No, this is not good.
How about this entire screen?
No, not the particular window.
Test.
Yes, yes,
Yeah.
yes.
What?
Now you can make it full screen. Yes, yes,
All
yes,
right. All right. All right.
yes,
Thank you. Sorry for the. All right.
yes,
So,
yes. Oh, yes.
good evening, everyone. My name is James Coe, and I'll be giving the first half of this presentation. I just tell you a little bit about myself. I think our host already gave some brief introduction. I'd just like to say that when I started out as a student, we studied all kinds of mathematics and physics equations, but I was too immature to really understand why we had these equations and where they came from, and why we worried about boundary value problems in particular. And if you take a course in differential equations or partial differential equations, you will always be solving boundary value problems. Well, later on, after I published one of my first papers, I got an email from someone, and they were asking if one of my algorithms could be used to compute or simulate light scattering off colloidal particles in paints and coatings. So these are sub-wavelength particles, or about the same as the wavelength of light. And this is called the Mie regime, M-I-E, after the name of a person who did this in the early 20th century. And so I quickly looked up Mie scattering in Morse and Feshbach, which is a famous mathematical physics book. And I had studied these things, but I had completely forgotten them. And then I realized I had to understand the mathematics of it in order to verify the algorithms that I was going to use. So then I became interested in boundary value problems and how to use these analytical solutions to verify algorithms that then one uses to solve practical problems. Okay, so let's go on now to the first slide. So to compute the interaction of light in arbitrary nanostructures, as you know, there's a movement now to make photonic integrated circuits. And just lately, there have been many conferences on photonic integrated circuits. And just lately, my colleague, Dr. Banerjee, and myself were at a conference in Ireland about this very subject. Now, to compute the interaction of light or the propagation of light in these nanostructures, meaning structures where the wavelength of the light is about the same as the features in the nanostructure, you need to solve Maxwell's equations, and you need to solve Maxwell's equations with boundary conditions. So you may have some channel in the silicon, maybe doped or changed in some way from the substrate. And then you need to solve, when you solve Maxwell's equations, of course, you get the polarization. So you need to solve the complete version of Maxwell's equations. And in a few cases, you can exploit symmetries and you can make analytical solutions, but usually they don't exist, and then you must use a numerical method. So let me show you a typical, one of the first problems I worked on, photonic crystals. So here we are. There is a structure. Let's see, can I get a pointer? No, maybe not. Anyway, on the left side, you will see light going in from a source, a source array,
We
and
can
it
see
goes
your
to the
you can see your cursor.
the
Yes,
cursor. I can use the
yes.
cursor. All right. So here's a source array. This is just some light, and this is the structure. The red is high refractive index, and the black is low refractive index. And then we shine light in the simulation through this structure. And then we detect it at the other end. And if you do this, you will find that there is a transmission spectrum. And so for most of the spectrum, the transmission is high. Then there's a place where it is very low and then high. So if you put light in at just this very wavelength where the transmission is low, then you can do some interesting tricks. And I will explain those a little bit later. But this is the kind of structure that you cannot solve analytically. Now, so here is what the photonic crystal does. We put light in. Now, in this area where these little dots are, they look like little dots, but they're structures. The light cannot propagate, so you send it in through this channel, and now the light can curve around a bend 90 degrees, which you cannot do in an optical fiber. And again, it's impossible to solve Maxwell's equations in this kind of structure. So I want to show you an analytical solution, just so that you can see how complicated it is. I'm not going to derive it. So here is an infinite plane wave of light. That's about the only thing you can model, talk about analytically. And it hits an infinite circular cylinder, and it's got a wave number of k. This is the wavelength. K is called the wave number. And now so we've got this polar coordinate system, and we have to match. We go from the wave equation. I'll talk about this a little bit later. From Maxwell's equations to the wave equation to the Helmholtz equation, and we solve the Helmholtz equation, and the wave field, the psi, I call it psi, and its normal derivative must be continuous across the interface. In other words, the field itself, psi, has to be continuous across this boundary. So this is a dielectric. The white is the vacuum. And then its normal derivative has to also be continuous. So this is a very difficult situation to satisfy, but analytically you can do this. And this was published by a person named Mee, M-I-E, that I discussed just a little bit a while ago in the early 20th century. Now it's maybe a problem in the graduate mathematical physics course. These are Bessel functions, and these are Hankel functions. And so you have this infinite series of Bessel functions and Hankel functions. So it's pretty complicated. Well, now, so let me just go to another problem before I. Now, if you replace the circular cylinder with a square cylinder, you cannot solve this. There is no solution. And why? Because at the corners here, there's no definition of a normal derivative. It could be this way or it could be this way. So you have to use some numerical method. Now, just show you what I did very briefly. We'll later on, we'll go into more details. But here are Maxwell's equations. You might wonder what happened to the other two equations. There are four of them, but the ones that are relevant to us are the behavior of the magnetic field and of the electric field. And you can turn this in each region of a uniform medium, except at the boundaries. You can turn the Maxwell's equations into a wave equation, and then you can turn the wave equation into the Helmholtz equation, and this is called Maxwell's equations in the frequency domain. And this is what is happening up here. You're solving the Helmholtz equation, and it's in the frequency domain. All right, but I'm not going to go into the details. All right, so there are two basic methodologies to solve Maxwell's equations that are used in practical problems. There's a time domain method and a frequency domain method. And what you saw here is a frequency domain method right here. So this is a frequency domain method. And if you are only interested in the final wave fields, then a frequency domain method is just fine, and a popular method is called the finite element method. And this is a numerical method to solve Maxwell's equations in the frequency domain. But if you want to understand how light really propagates in real time, well, in algorithmic time, which is related to the real time, then the finite difference time domain method is a very excellent method, and there are many advantages to it. And later on in this series, we will explain why this is so. But for now, just take it from me that this is a very good methodology. Now, I'd like to diverge into a little bit of philosophy, because as we go on, we're going to model physical systems. You cannot solve most physical systems or understand them in their entirety. But what you can do is you can take the most important features, the most important characteristics of a physical structure, of a physical problem, and abstract it into a model. And a long time ago, well, I shouldn't say a long time ago, but in the 1960s, a very great physicist called Wigner, or Jean Wigner, discussed the unreasonable effectiveness of mathematics. And I'm going to talk about the unreasonable effectiveness not only of mathematics, but of models and data. So this is Wigner's paper in February 1960. I think he had talked about this in the 1950s, but it was finally published in the 1960s. And when I was a student in school, I was learning mathematics, algebra, and about Newton's laws. And here we've got the famous Newton's equation, force equal mass times acceleration. And then a little bit of algebra gives you acceleration equal force divided by mass. And I always wondered why this was so. And well, Wigner had explained, well, he pondered this question. Well, models too can also be unreasonably effective, and I'm going to show you this in a moment. And as early as at the 1200s, William of Ockham was thinking about models. So he was a monk. He was an English philosopher and a Franciscan friar. And he defined what a good model is, that it should be simple, it should not have too many parameters, and it should also predict things that the original model did not explain. So it should predict new phenomena. And I'm going to discuss this. So one of the very first triumphs of logic and modeling was this. So this was an old-fashioned picture of how Atlas holds up the Earth. So there was a philosopher called Anaximander, and he did some reasoning. He said, well, Atlas holds up the Earth, but now what holds up Atlas? Well, so maybe there's another Atlas that holds up the first Atlas. Well, what happens? Who holds up the second Atlas? Well, here we are. You have another Atlas. Well, this is called reductio ad absurdum. In other words, you need an infinite number of atlases, and so this can't be true. This is very complicated. It's absurd that we would have an infinite number of atlases. So it's too complicated to be true. And so in 610 BC, somewhere around 610 or between 610 and 646 BC, Anaximander of Miletus, that's a little island off the coast of Turkey, which was a Greek island, and it still is in those, I think. He concluded that nothing holds up the Earth; it floats freely in space. So this is a real triumph of logic, and time after time in scientific history, we have found that logic and models can do very well, incredibly well at predicting real phenomena. And Penrose thinks that structures such as logic and mathematics exist independently of the human mind. In other words, I suppose Penrose, I'm not sure of his religion, but maybe he would believe that God has created this kind of mathematics and we're just learning it. And he has a very interesting book, if you would be interested to read it, The Road to Reality. It's really a very sophisticated mathematics book, but it discusses a lot of philosophy. So anyway, I would like to say that it seems to be a law of nature that ugly, complicated models fail. And I would also say nature abhors a mess. And I want to show you a mess. So let's think of a very simple equation, the simple harmonic oscillator. Here it is. So you can solve this analytically. You don't need any kind of numerical method, but I'm going to show you a numerical method. So here it is. This is called a finite difference time domain equation, and I'm not going to discuss this in great detail right now, but this is the state of the oscillator. Psi is this oscillator position. It's just the position of the oscillator on the, say, the x-axis. This is a time step t+1. I use tau because it's discretized time. This is a time step at t-1, so before the present, and this is the position of the oscillator at the present time, so time t. So this is now, this is one step before now in the past, this is the future. And so this is the model of this differential equation, of this partial, it's a differential equation because we don't have time in it. And so the error is proportional to the time step squared, and then the fourth derivative of the position. Okay, so this is one model, and here is a fourth order approximation, and it's much more accurate. The error here, it's delta t squared over 12. Here it's delta t to the fourth over 90, and it's the sixth derivative of the position. Well, there are questions you might ask about this, because what if the derivative is greater than 1? And what if the time step is greater than 1? So it's got to be less than 1, of course. All right, now here is the algorithm to solve the second order algorithm. It's very simple, isn't it? It's simple, but it's not very accurate. And so these little dots here, the red line, the black line is the analytical solution. And now here is the more exact model, but it's much more complicated. And in fact, it's numerically unstable. This line here, this colored line, maybe on the screen it looks black to you, but it very quickly, after a few steps, it diverges from the true solution. So it's a terrible model. It's mathematically more accurate. On paper, it's more accurate, but it's not more accurate. It's much worse. And I'll just tell you one reason why. There is and I'll explain this later on in subsequent discussions, but this is a second order, where the harmonic oscillator is a second order differential equation, and we have what is called a fourth order model. And you cannot solve a second order differential equation with a fourth order model. The differential equation requires two initial conditions, but this fourth order model requires four initial conditions. And I will discuss this later, but not right now. Now I'd like to show you a model. We saw the photonic crystal structure, and here is the photonic crystal, and maybe you noticed that these little red areas seem to have different shapes. We have it on a numerical grid, and you might, if you look at them very closely, depending on their position, they could have these different shapes. However, for the purposes of the calculation, this is fine. We don't need to model this any more accurately. We don't need to make a shape that looks circular because we are in what is called the Rayleigh regime. In other words, the cylinders, these little cylinders, are small compared to the wavelength, so the light does not see these irregular shapes. So this is a model of the photonic crystal, and this works very, very well in getting the correct transmission spectrum. Now, I'd like to show you, I said that models, if they're good models, or I should say, I didn't say, but Ockham said, I mean, this fellow up here, let's go up here, this fellow here, Ockham, William of Ockham, in the 1200s, somewhere between the 1200s and the 1300s, said that a model should predict new phenomena. Well, if you ever read the electromagnetics book or electromagnetism book by Jackson, a very famous author, and his book is very complicated, and he talks about precursor waves, that if you shine light through, say, a block of glass, of course, the speed of light is slower in the glass than in vacuum, but a very small signal will actually go through the block of glass as if it were propagating in vacuum. Now, here is a finite difference time domain calculation of a wave spreading out in vacuum, but I've set the speed of light below its vacuum velocity here. And so now what you will see is this black is the main signal coming through. And these little dots here, this is greatly magnified. This is scaled up by factors of 10 to the 7th, 10 to the 8th, 10 to the 9th. I forget it. Well, here we are. It's somewhere around 10 to the 15th, scaled up. So it's a huge scale up. And I hope this will work. Can you see? Yes, let's see if it works. I believe it will work. Yes, okay. So we've turned on the light source. And so the main signal is propagating with the speed of light in the medium. But on either side, this precursor signal is traveling. And again, it's greatly magnified compared to the black here. So, and I don't claim that this really gives you the analytical result that Jackson derives, but phenomenologically, it predicts a precursor wave. So again, this is the power of a model. Okay, another model, my colleague Dr. Banerjee has looked at this in much more detail, so I just want to give you a flavor. There are many insects, or many birds too, many living organisms, let us say living organisms. In particular, though, we looked at a butterfly called the morphoretinor butterfly, and it has no pigment in its wings. The color of this butterfly is completely, it's called structural color, and it's completely due to diffractive effects. So here are various views. You have these scales. Here's one scale, and then this is the microstructure of it. And by modeling a kind of average microstructure and making a number of similar simulations, we could predict very closely, or I should say, get a very close result to the experimental result. That is, people have measured the reflection spectrum and off of this butterfly's wings, and we could get a very good result. So as we proceed through this series, we're going to talk about models and optimizing the models to give good solutions to Maxwell's equations. And not only solutions to Maxwell's equations, but also to the structures, where we're looking at how light propagates through complicated structures, how it interacts with complicated structures, and we cannot model those physical things in their full glory. So we take the most important features and model them. So this is where we will be making many kinds of models and optimizing them to give us the best results. So I'm going to just summarize, and before I turn over to Dr. Banerjee. So this is the summary of what I've discussed. So we're going to discuss the design of optical and photonic components and new modeling and computational methodologies. And I've just given you a little bit of a flavor here. And I just want you to keep in mind that some of these models may seem strange or mysterious, but they follow a certain kind of logic, and they can be unreasonably effective if you do this modeling correctly. And I'd like to show you that models have been successful in many fields of science and engineering. So perhaps I studied particle physics, so but maybe you heard of the quark model, which is we know that protons and neutrons and other particles have a substructure, and the proton is made up of three quarks. And this was just a model, and no one believed that these really existed until they were found. And then a few years ago, the Nobel Prize in physics went to Peter Higgs, and that's why it's called the Higgs model. And he made a mathematical model, and maybe later I might just show you what it is. But the Higgs particle was found just a couple of years ago, and nowadays I'm doing a lot of work in superconductivity for quantum computing, and there is a similar model called the Landau-Ginzburg model, or Ginzburg-Landau model, perhaps. And it actually has some of the same features of the Higgs model, and it's a very successful model for understanding superconductivity. And then finally, this is what we will be more concerned with in this series, is the finite difference time domain model of the wave equation and Maxwell's equations. And as my colleague will explain, that there's many levels of sophistication to really get good results. And so we will show you some of these very effective models as applied to computational photonics and electromagnetics. So with that, I think, should we ask any questions now, or we want to wait till the end?
We can just a minute. We can wait until the end, and also, if you allow me, I'll just put three short three short questions before you,
Yes, of
Saswatee,
course.
Dr. Banerjee starts. Questions means it is not actually that way questions, because I have not studied these subjects deeply. So three points just came to my mind when you just touched that harmonic oscillator. So
Yes.
harmonic oscillator, that potential function, is it a self-reciprocal function like self-Fourier function?
No, it's just think of a pendulum. That's a kind of harmonic oscillator. Or think of a weight on a spring, so it's bouncing up and down. That's a simple harmonic oscillator. You assume that the spring is linear, so that the more you stretch the spring, the more force it pulls back, and that's mostly true. And with a pendulum, if the swing of the pendulum is short, not too, I mean, it shouldn't be swinging 90 degrees back and forth, but say 10, 20, or 30 degrees back and forth from the vertical, that will be a harmonic oscillator. So yeah, maybe let me just very briefly. So this is the what is called the angular frequency, and so uh, so it's 2 pi divided 2 pi times the frequency, the back and forth motion. And I should have maybe explained that a little bit better. And so this has an exact solution. It's either the sine of omega t or the cosine of omega t. And so you don't need any model or finite difference method to solve this problem, but it's a good problem to look at because you know the solution in advance, and then you can test your algorithms. And this is always a good thing to use your algorithm to solve a simple problem where you know the solution. And then in a case where you don't know the solution, you can believe, but it's not always true, but you can believe that if you got the correct answer on the known problem, then there is a good chance that it will correctly solve the more difficult problem.
Okay, thank you very much. And one point, when you just showed that butterfly wings, I just came to my mind. Is there any application in the dress industry? That fabric industry, that the clothes having these type of nanostructures uh, could produce different colors, or already it is there? Have you heard or seen?
Yes, you asked a very relevant question. I haven't seen any clothes with structural color, but I do know that people are actually discussing making such clothes with structural color and other kinds of objects with structural color. Yes, indeed, there is a great interest in this kind of thing. So there is, in fact, a commercial application to this. And so what
Yes,
you would like to do is you would like to design structures like this. You could
yes.
actually nowadays we can actually fabricate things like this. So this is potentially very important commercially.
Okay. Thank you very much. So, please, Dr. Banerjee, you can start your part of the introduction workshop, part one. Okay. Please, over to Dr. Banerjee.
I have to stop. Let's see. I have to stop sharing.
Just a minute. So, we are having the part one of the introduction, that computational photonics. Dr. Saswatee Banerjee is preparing to show her presentation part. And if anybody has any question, please raise. So, I'm only looking at somebody shown one comment. So we'll show the presentation of Dr. Banerjee when she is ready. So this will be a three-part online mini workshop on computational photonics, and this is the first part. Professor James Cole presented the first part, the first section of the first part one. Now Dr. Saswatee Banerjee is preparing to show her presentation. Please be with us. We'll show it soon. as she is preparing to share her screen. Okay. Okay, you can make it full screen. Yes. Yes.
I did. I stopped.
No, no, no. This one stop.
I stopped sharing. I'm not sharing anymore. My video is on.
Okay. No, no, no. Oh God. Again, I lost it.
Go down to the
Sorry. It's not sharing.
Is it? Okay. You can just quit and rejoin from your laptop and try it.
Okay. Can you see my screen then?
Yes, yes, yes. It is coming. Yes. Yes. Make it full screen.
Can you see my screen?
This one is the first one, computational photonics and introduction, part one. Is it the
What is
presentation you
happening?
are starting?
Hello.
Yes. Just a minute.
Well,
I think I can see your screen, yes.
can you see my?
I think I see it, yes. I think
I cannot do this. It's just not doing it. Oh, wait 1 second, please.
you had it
Yes.
earlier.
Yeah, no, see. Can you see my screen?
We
Yeah,
can
it's
see that
here.
computational
It's there.
photonics and
But I am
introduction
not
part one.
hearing from them.
No, no. Can you hear
Unmute
me?
your,
You cannot hear
don't
me?
go off. I mean, unmute your,
Oh,
unmute your,
oh,
You can't
yeah,
hear me?
that's the problem.
ah.
There you are.
Oh, yes. Can you see my screen now?
Uh, this is that, yes, this computational photonics and introduction. It has come, part one. Yes.
Yes, but I cannot go to this thing,
Where?
the slideshow basically mode. I'm not sure
No,
what is
slideshow means
happening.
it is your screen. So you can press that F5.
Hmm. See if you can see my slideshow. Can
Yes, yes,
you?
yes, yes.
Yeah,
Oh,
it's
great.
there. Okay,
Thank you.
we
Thank you
got it.
very much.
Okay.
I'm sorry for all the little technical trouble. Uh, Thank you very much for joining. And hello and welcome, all of you. So, today's, presentation, my purpose here was basically to uh, get an interest, to generate an interest and to share with you my own journey in this field. And I mean, when I started my career, I was in this, I joined this applied physics department in Calcutta University. And somehow this, at that time, I really did not know what this optics is all about, this special topic optics is all about. But then I talked to some of our professors before starting, and then it's, I mean, somehow the light and the visual quality of it, that is the color, the displays, that attracted me a lot, basically. And I still have that love for optics. And that's what kept me motivated and kept me going in this field. So I think when I mean, joined the group, I remember, I mean, when I joined this applied physics department in Calcutta University, Professor A.K. Chakraborty, I think he was at that time our department head, and he gave a little speech. And he said that if you are doing applied physics, jobs will chase you. You won't have to chase jobs. And I think, I mean, there is a, I mean, of course, you have to take the trouble to get a job. But the thing is, applied physics is something that gives you that applied part. That is, you want to solve a real world problem, basically. That's one thing that, again, that was very interesting for me, that it's not just learning something theoretically, but you use those principles and you actually are able to solve a problem. I think you heard the talk by Professor Cole, and he was discussing about the modeling, etc. Now, when I was an undergraduate student, I was in physics honors class, and I remember the electromagnetism that I was taught. Actually, I saw this, our professor came to class and he wrote some boundary value problem, and he said, solve this boundary value problem. Now, I had I did not feel any interest in solving these boundary value problems, because to me it was just a meaningless thing. It's just a little equation, and what it does, I did not know. So that was my approach. But slowly, once I started this optics photonics course, and then as I went through my career, I learned a couple of things. That is, you can make this same boundary value problem, you will find out later that it can actually help you to solve serious real life problems. So that's something that understanding, that my understanding in my career or in my journey, I would like to share that feelings, or that my understanding with you, basically. So here, what I mean, starting with is basically why you do this nanophotonic design simulations, etc. So one of the problem with this field is we are dealing with very small structures. It is wavelength scale or subwavelength structures, actually, most of the time. And what I mean by subwavelength, I'm talking about the visible domain of electromagnetic spectrum. So meaning that is about 400 nanometer to 700 nanometer, the wavelength, okay, from blue to the red. And then, so when we are talking about these nanophotonic structures, actually, a lot of these things are about 100 nanometer or less, or around that region. So when you are dealing with these structures, in fact, the fabrication, the people who are involved in fabrication processing, you can, I mean, you have seen yourself that it is very difficult to basically fabricate. Even with nowadays, things are becoming far better, but even with that, fabrication is still very expensive, very costly. Actually, I saw, I mean, in a project, then we were trying to fabricate some diffractive structures. Now, the person who's designing did not, I mean, he was designing with some wave optics based tools, And these tools, these are more with scalar field theory, so they don't really apply, or it doesn't really give you the actual results what you expect in this particular case. So, and then he was, from that point of view, he was going into this kind of fabrication which was really costly, very expensive. And so actually the fabrication could not, I mean, we could not go into fabrication. So then I started working with this electromagnetic solvers and uh, finite difference time domain. We'll come to that, but more like vector field theory you need to apply to solve these problems. Basically, that's what I'm trying to say. So some of these problems you really need to solve the vector field theory. That is the Maxwell's equations. You really need to solve the Maxwell's equations. So that's one thing that I'm trying to talk about here. That is, you need to, there are several aspects of it. I mean, simulation means one of the reason you do the simulation modeling because you want to predict the behavior of this particular device. And you want to also, when you go into fabrication, there is a, I mean, you go back and forth between your simulations and your fabrication, because unless you feed back your data into the fabrication process cannot be refined, basically. So this is a very important aspect. If you really have to go for photonic, say, for example, at this moment, photonic integrated circuits are a very big field, basically. So if you have to go into that direction, you definitely need the photonic simulations, design, modeling, that kind of thing. So that's what I was trying to say. So now if we go to the next slide, this is a little my background, my own background. I did tell you that actually in Kolkata University, I mean University of Calcutta, the Department of Applied Physics, where I started my journey in optics and photonics. But then I did my PhD there in applied physics, and there I worked on macro optics, basically, and this macro optics involving lenses, basically, and then the design of lenses. So that taught me something about nowadays you hear a lot about inverse design. Actually, that's a very important point. But this inverse design, you do use some optimization techniques, etc. So that's where, this is where I learned the computer modeling, or the methods, the computational methods that are very useful in design, in simulation, etc. So I will show you a little bit. Now here you can also see that I wrote my slide. I have a lot of Japanese in this because I spent a long time in Japan. Actually, after I finished my PhD, I mean, even just before I actually submitted my thesis, I got a scholarship in Japan, and this is given by Monbu Kagakusho, that is the Japanese Ministry of Science and Education. And so I went to Professor Yatagai's lab in Tsukuba University. And so the reason I put this Japanese, when I went to Japan, I did not know any Japanese. And it was a real difficult life, in fact, because anybody who went to Japan, you will know that if you don't know the language, it can be pretty difficult. And then it was my life, this was my first-hand experience living as an illiterate person in a country. Because in my country, I was considered, in India, I was considered highly qualified, educated. And then I went to Japan, where I became just illiterate in one day. And then I could not read anything. So there, I took the trouble, and I have to thank Professor Yatagai a lot, because he's one who pushed me. He told me that you definitely need to learn Japanese. And that was really a very good advice. And I cannot tell you how much trouble I took to learn any Japanese, but I did take the trouble. And I would say that that was a very good thing that I did, very good investment. Because what it is, in fact, another thing that I learned staying in Japan and working there for 20 years, I spent 20 years in Japan, and I have fond memories working there. And the thing is, you won't be able to appreciate the whole thing unless you understand the language. And another thing I noticed, that in fact, yes, people will teach you keigo, they will teach you konnichiwa, but what they won't teach you is the technical Japanese. That is, I mean, your topic, the Japanese that is needed in your topic. So this is something I learned through a lot. But that's why I put it in Japanese, to show that yes, I can do some technical Japanese. And so if any one of you are a little bit interested in technical Japanese to learn and to say translate or something, I can be helpful on that. So here, what I was trying to do, so what I did in Japan first, I mean, in Professor Yatagai's lab, where Professor Yatagai actually introduced me to Professor Cole, and then we started working together. And that was in subwavelength optics. He said that let's work in subwavelength optics. And I actually went through first, I actually was trying to read a book by Taflov that was at that time published in Finite-Difference time domain. And I have to say that I really did not understand anything. And so I really felt that, okay, this is not something that I can do. And then I realized that because of Professor Cole, and there was a whole team, so I met a lot of people, I talked to different people, and then we started working together. So this is where, I mean, when you do things yourself, you learn something. You see things very differently, actually. So, okay, before going into that, I will say that then after I finished my PhD from Tsukuba University, this was a second PhD in applied physics with this wavelength optics, basically focused. And then I joined the industry. First, it was Sumitomo Chemical. It is a huge company, and it was very good time that I spent there. And I was working on liquid crystal displays. And then, as I said, actually, optics for me, it was more like the visual side of it, the display, etc. It attracts me. So I went into this liquid crystal displays, and you see, looking at this computer monitor, you think, okay, oh, you're seeing things, and it is such a thin display. But actually, behind the screen, there are multiple optical components that makes this display possible, in fact. So if you go into the details, you'll see, and you will be really surprised to know how much of optics goes behind the screen, basically. And then I did some work with LEDs, different kinds of LEDs, basically polymer LED, organic LED, then the micro LED, inorganic material LED, etc. So I will little bit talk about, just to give a flavor of the things, of the different, as I said, that as an applied physicist, I really enjoy this ability to solve a real life problem. So I would like to give you a flavor of this kind of things. I mean, where these principles really apply. And here, so this is what I was trying to say, that we will talk a little bit about the modeling simulation that contributes to the design and fabrication of photonic devices. And what we are seeing here is how light interacts with media and structure. Yes, in nanophotonics, this is another thing. The way we control light is, there are two aspects of it. One is the media, the different kinds of materials, and there is another is the structuring of these materials, because that really determines how the light is going to interact with a given device, basically. So here, this is a little bit of a repetition of what Professor Cole already talked about. Yes, I will say that, as I said, that there are times when you really need to solve the full vector field theory, basically. What that means, it means the Maxwell's equations. And not all, there are four Maxwell's equations, as you know. The two of those, that is the Carl equations, basically, that's what we basically try to aim to solve for most problems. There are reasons, I mean, there is physics that determines which, I mean, which problem needs what kind of solution, basically. But actually, the Maxwell's equations have different forms. One is called the differential forms that we are more going to work with. But the thing is, there is also this integral form. And then, as Professor Cole also mentioned, that there are host of solution methods. I mean, you can solve it in frequency domain, you can solve it in time domain, etc. Now, the question is actually, if you think about it, a lot of problems in optics, actually, you don't really see the transient phenomena, or you don't even measure, or you don't even care about the transient phenomena. What you really care about is the steady state behavior. So, from that point of view, actually, why not use this frequency domain method? You would think. And in fact, that would be the straightforward thinking. But interestingly enough, in my career, what I saw, in fact, it is pretty difficult to use the frequency domain methods to solve the Maxwell's equations for complicated structures. So, the finite difference time domain method, the attraction of this method is when you are dealing with a complex structure with various material boundaries, there are interfaces between different material media. That's where the things become complex, because there are, if you know the electromagnetism, there are electromagnetic boundary conditions that you need to enforce at each boundary condition. Now, this is when you are dealing with the frequency domain methods, what you do is you do enforce those actually through some matrix manipulations, etc., which is not easy to do. But here in FDTD, once you have this time marching established with your initial conditions, it will automatically implement those material boundaries. So that is a huge thing, because that allows FDTD to be implemented in a stable form, basically, as particularly for 3D implementations, etc. This has become the industry standard in my, career I have seen. So here on the left hand side, I will show you a little, demo. This will show you how light is propagating and what you can see in real time. You see, this is a very simple structure. It's not a big issue, but it's a what this green thing is. It's a high index material, and you can see the surface structuring on top of it. And now you have a little point source here. So light is coming out of the point source, and you can see in real time how it propagates and how it interacts with the interface, basically. So that gives you an intuition, and that gives you an understanding of the physical principles, or how light really propagates in a medium. It's not about writing a boundary value problem in this board. If I write a boundary value problem, you'll say, it's not interesting. Come on, what are you talking about? But if I show you this, then you immediately know, oh, yes, this boundary value problem can do this, can tell me how the light propagates and how it interacts with my interface. So that's what it is. So, but there is a lot of complex physics under this little picture. So now if we go a little bit farther on this topic. So this topic was actually, I was trying to do this thing because there was, in Japan, this is one thing that I really loved about Japan, that there was a lot of academic and industry collaborative projects, basically, which I thought was very good. So here, this was an LED structure, basically. So what LEDs do, without getting into too many details, because there are other details, but the thing is, here you have an high index medium. More or less, it involves a high index medium. So the challenge is to get the light out of the high index medium. As you know, that when you have the interface between high index media and air, say, for example, you see there is a critical angle, and then light will be totally reflected and you won't get it into to propagating in air. So to do that, you need to do some surface structuring. You can do, there are many ways of doing this surface structuring. So this is called extraction efficiency, and this extraction efficiency is a big topic, especially in case of LEDs, when you are dealing with LEDs. So here, what you can see, this is a small demo, basically, small explanation. You can see these are all done with this so-called non-standard FGD that is pioneered by Professor Cole and his, friends and his colleagues. So this was done by using those, and these are our own programs, our own codes that we do. I mean, you might tell me that, oh, why should we care? We have this commercial software, we can click on it and it will do. But you see, when you do things yourself, you see so much better. You understand, you get this insight so much better. So that makes you more interested in the problem. So what you are seeing here is that various types of grooving or various types of, say, grating structures have different kind of effect. That is, you can see that definitely for sure that when we have a surface structuring, we're getting more light out. Now the question is here, based on the kind of structures, grooves, the aspect ratio, you can see that light is going in different directions, how much light is coming out. All these little factors are dependent on the kind of structuring you are doing. Now, here, one thing we need to understand that, I mean, for LEDs especially, if you don't do anything, normally they have this Lambertian output, basically, so meaning equal in all directions. So sometimes you need to control that. Okay, so that is another effect that you might want to channel it within some collection angle or something. That is also another aspect of it. So all these little control, so you really need a lot of designing there. So you need this kind of modeling. That's what I'm trying to say. However, this is not a perfect model here. What I did here is actually a plane wave. I had a little plane wave coming and it is hitting the boundary or interface. But actually in LEDs especially, you won't do that. The reason for that is it is an electroluminescence effect. It does, in fact, what you are seeing is fluorescence. So you can do the energy diagram and you can see that the radiative part, you want to maximize the radiative part, etc. And without getting into too much details, I mean, maybe in the next, if there is more interest, I mean, in the next part, I can cover a little bit in more details about these things. But the thing is, normally you need to use all directions. Basically, you need to look at all directions. It's not just one direction. So you have to, it's more like we use point sources or the dipole radiators, basically. So that's how it is done. But this particular example is a very simple example, but it is showing you the effect of surface structuring, basically. And this is all done, I mean, by, someone not so great at these things by me. So this is where I will show you, this is a this little bit of extension of this thing, that is the organic LED. So you see actual LED. Now, before you saw, this is just an interface between a high index medium and a low index medium. However, in an actual structure, as I said, that there is a radiative part and the non-radiative part, and you would like to maximize the radiative part. So it's a pretty tricky balance, basically. There is a lot of things that goes on into the material side. So you have, of course, these are the basic materials that you use, in fact, and basic layers that you use. Now, what I'm trying to say here, is also that, for example, in the left-hand side, you can see that this is basically the stack of layers. When you have a structure like this, you do have some commercial softwares that can actually solve this problem, and you can do it. However, when you are a little bit more innovative, creative, etc., you do a little bit different structure, say a curve structure. Now the problem is you cannot really solve with those commercial, package basically, because here you see on the left hand side, what you can do is you can exploit the structural symmetry, while on the right hand side, you cannot do that. So what you really need is you need a numerical method, which is FGTD here. This is my own, programs and my own calculations, this one. So you actually ultimately, this is done in 2D. The picture that you are seeing is in 2D, but the point is it actually needs a whole 3D solution, in fact. And here on the in the middle, what you are seeing here, that as I said, that normally you use the dipole radiator. So what you will see here, this dipole radiator, it is actually it is oscillating along this y direction. So it, in fact, its major emission direction is perpendicular. So that's why you see the light coming out. The thing is, if you take a dipole that is oscillating in a perpendicular direction, you will see most of the light is actually guided through the structure and very little will come out to the air. And these are very important points when you are really doing the simulations, LED simulations. These come out again and again, and it's a very important problem to consider. So the problem is what we are trying to understand, and what we understand from here, that there is a dependence on the polarization, basically, of the molecule that is radiating, in fact. So that's what I was trying to explain from this. Now, this is totally a different problem. So I think Professor Cole did mention in his presentation that there is something called this me theory. Now, unfortunately, me theory is a closed form solution of Maxwell's equations. That's fantastic. But this analytical solution is only available when you have a perfectly circular cylinder, infinite cylinder, or you have a little sphere. Now the problem is complicated when you have multiple particles. Now you want to see the interaction between multiple particles. When you have this, for example, here you can see there are two nanoparticles and they're coming close, they're coming farther from each other. And on the right-hand side, this is not a video, but this is more still, but you can see actually, depending on the incident light and its polarization, how it compares with the arrangement of the particles. Actually, the peaks depend on that, the resonance peaks, or this is from nanoplasmonics. And so the LSPR modes depend on that. And what you can see that in one polarization, you can in fact tune the resonance peaks. So these have some applications. For example, there were a lot of work, there's a whole body of work in trying to use these to change, the Purcell factor of the cavities, to influence fluorescence, to boost fluorescence, etc. There are many such, work basically. In solar cells too, there were a lot of applications. People tried to harness these properties. But in any case, the point is when you have a collection of particles like this, there is no closed form solution. So what you need to do is you definitely need to use some numerical method to solve. And as I told you, that FDTD is a good way to basically, it allows you to implement the algorithm to solve Maxwell's equation in a stable manner. It gives you a stable algorithm. So in any event, but in this particular case, I have to say that there's more complexity here. as I told you in the beginning, that there are two things. One is the material and one is the structuring. In fact, the plasmonic modes are decided by both by material and by the structuring. So now, when you are dealing with these metal particles, etc., you will see that they have a very different response. They have a very different, dielectric properties compared to the dielectrics. So that determines how the Maxwell's equations look like and how you solve those equations. So that's the more details, but without going into the details, we can still see that how they interact. So this is the power of physics, that we are using some physical principles and then we are trying to solve some real life problems. Now I will go to the next slide. So here also, this was a work that I did, and there's a lot of actually applications of this. I recently saw a paper. Okay, before I go to that, let me explain what I was trying to do here. This is a polymer matrix, and then you have nanoparticles dispersed in it. And so you can see, you can calculate, for example, you can do the Mies scattering, just single particle, you can do it. And we actually prepared the samples, we did the TEM of it, and we measured. What happens is when there is cluster formation, you see, there is it depends on how you control the concentration, etc. But once there is cluster formation, there will be, the properties will be very different. You won't be able to just apply Mies scattering and be done with that. Then you have to take this cluster, the effect of the clusters, and that's where you need the finite difference time domain or that kind of numerical models, basically. So I did here that kind of thing, and we actually worked with samples, etc. Now, I want to say that very recently I saw a paper where they're using this kind of film as anti-reflection coating. So there are serious applications of these things, in fact. So this is a place where you are using these complicated mathematical models, etc., to solve a real life problem. Now here, I think Professor Cole already showed you that the photonic crystal, etc. So what we did, I did the 3D version of it. So you can see there is this bent waveguide. This is the defects. You can take out some of these posts and make a channel. And what you can see, these things are used in, with fiber communication, etc. And the thing is, what you can see here, that there's very little leakage around you are sending the light. This is a pulse, actually, pulse of light, and you are sending it through this bent channel, but then there's very little leakage, in fact. So this is the power of simulation, that the simulation is showing you that, you can get into fabrication because you might expect very little, in fact, very little loss here. And also, you can actually calculate the dispersion of the pulse, etc. I think there's a lot of calculations, and Professor Cole can another day explain what they found in their paper. So this is square PC, but then you can also do these hexagonal structures, and this is a straight channel where the light is propagating through the straight channel. So I won't go into all the details at this moment, but these are things that we did. Now, regarding this butterfly thing, whatever I did in this butterfly, that is in the paper available, so that's just fine. But I took a little bit different approach than Professor Cole's team. So this is actual structure looks like. So in fact, I did some computer generated, structures like this. And then you can have some variations of the structures and you can calculate. The point is, I have noticed, in fact, just exactly this structure you don't need to do. The structural color, the point about structural color is, this is another way of producing color. So you can bypass the chemical pigments or the chemical dyes, that kind of thing. So this is another totally different way of producing color. And then very recently, I noticed people are using phase change materials basically to design dynamic or tunable color basically, and you can do it with the Fabipero structures and that kind of structures, in fact, which is much easier to do than this. But in any case, so that is a I mean, significance of studying the structural color, because structural color is very important for displays. And as Dr. Chaudhary mentioned, that it's also a coloring technique basically. So this is another little thing that I worked on, and I have a lot of fun working on this. This is the CMOS image sensor. So what it is, that it's basically a detector. So I talked about a little bit about the LEDs where light is emitted from a structure. And here the problem is reversed. That is, you have light incident, and then in the you see there is a photonic silicon photodetector here. That's the major point. Now this photodetector absorbs, its duty is to absorb the light, in fact. And then this absorption, this is called optical efficiency, then it will be converted to quantum efficiency basically. That's the point here. And those who of you have used, for example, CCDs, etc., CCDs are, I think, more sensitive, most likely. And then the next version is the CIS, basically CMOS image sensors. And in Japan, I mean, Japan is one of the leading nations where this CMOS image sensors are very good and well researched and well fabricated, in fact. So these are basically they come as in your recording plane of say digital cameras. These things come as pixels, and so the resolution depends on the pixel size. So the problem is, as you have more smaller pixel sizes, you need more complicated modeling and design and all that. Now here you can see that there are these multiple layers, and then this micro lens, the substrate, etc. These things have their effect, in fact. And you would like to design them very carefully, because one of the problems affecting these designs is called crosstalk. That is, when you have multiple pixels or the pixel array, light can go from one pixel to another, and you would like to stop that. So to do that, there are many different, techniques that you do, and which technique is more effective than other. To understand that, you need a lot of modeling, a lot of serious modeling, basically. So if I go to this is done with the commercial software, and which a lot of people love this, and I think it is a very good solver, basically. It actually, when you go to the 3D, and if you are dealing with the complex structures, you need a lot of things. You need to really have the parallelized algorithm and things like that. So yeah, it works pretty well. It's more stable, I noticed. So this is what happens. So you have green light coming in, you have a green pixel, you have a red pixel. As you can see, that the green pixel really allows the light to be in, and then it gets absorbed. But the red pixel, because you have the red filter there, it cuts a lot of this light, and that should be its job. However, it doesn't do a perfect job, because these filters have bandwidth, wide bandwidth. So there's a lot of things you can do here, basically, and you need to study those things. So this is one of the things, that a practical problem that is being solved with FGD. Now, in fact, I would like to mention that the researchers before, in fact, they use these geometrical optics principles. They use ray tracing to solve this. And you can see there are plenty of papers, they point out that the difference between the ray tracing results and when you are coming to this FDTD simulations, more rigorous simulations, you can see the difference in results basically. So it's again to stress the point, to more emphasize the point that in fact in some problems this is you cannot escape, you do have to solve the Maxwell's equations in its full glory basically. So that's one of these problems. So if we go to the next one, this one okay, this comes from this LED, I mean not LED, but LCD, the liquid crystal display, basically. So here there is something called a DBF, or the brightness enhancement film. Basically, this is well known, and this was done. This is one of the paper, this science paper, and they did a very good job. However, I did a little bit of calculations here. And what it is doing is one is a uniaxial material and another is a isotropic material. As I said, the Maxwell's equations takes different shapes when you change the material. And then in this particular case, luckily, you can, because of the symmetry of the structure, you can solve analytically this kind of, I mean, stack of thin films basically. And then from solving that, I got a stack which will behave like this. I think this is the reflectivity that you are looking at. So it will be a filter in 3 different wavelength bands. So I managed to do that, but this is a special case. But another thing that I wanted to say, because I think I did tell you before, that this inverse design. So here it's not just the doing the electromagnetic part, you also need this part, this design part. That is, you need the optimization algorithm. So here you can talk about a lot of different kind of options that are available nowadays. And of course, the local optimization, the global optimization, etc. But this is one method that I really liked, that is the genetic algorithm and global optimization. I have seen some people using it for metal lens design. I mean, it was in ACES conference that I saw some people doing that. And I show you how it starts with multiple solutions, but then you will see that the best fitness is coming up, and it will be selecting the best fitness. You have different strategies, but some strategies can perform better than others. But GA is kind of robust method to do this kind of thing. So in any case, I just wanted to point out that this is another part of this computational side of it. That is, you do need to be aware of the optimization algorithms and their use, how you use in a particular problem. So we do that. And finally, last but not the least, as I said, that one of the reasons I chose optics, because I am very attracted to the visual, the display part, the light is attractive to me, the color part. So very recently I started drawing. And this is actually an oil painting, not totally finished at that time, but I liked it because it is depicting the spring when these flowers come out. So this is after winter, especially in these northern latitudes, you will see that in winter, bare trees just shed all their leaves and all that. And then in winter, when these flowers come out or the new leaves come out, in fact, if you notice, a lot of new leaves are not green, they're red. And that was something that I found out myself after all this time. And that was very interesting to notice. So I thought, okay, this is a new beginning, a new phase, etc., to signify that. So I decided to draw this. So I liked to show, and to me it was very appealing. So in any case, thank you very much for listening to us.
Okay. Thank you, Dr. Banerjee, uh, for the enlightening part you have shared after Professor uh, Cole. It gives actually a picture, not only the last picture, but it has given a picture about how the curious mind, from starting from, say, in college, in bachelor's studies in physics, and then that when it is flowing to the master's program, one PhD in, as I know you have done in optical design, lens design. So a lot of programming also, and eventually you studied Maxwell's equations, which we most of us never actually did. So that rigor gave you an opportunity to look inside the phenomena of light flowing uh, in vacuum in some media, and also inside some and reflection and diffraction from nanostructures. So it is beautifully mentioned. I hope that will appeal to the researchers, since LinkedIn is a platform, and also in YouTube it is streaming. I have seen, I've checked, some people are watching, some people are just keep leaving some comments. So when we see at the comments, it means some people are interested. So let us uh, view the comments, and please bring Professor Cole also in the screen, and if
Hmm.
he opens the my camera.
Should I open the camera then?
Hmm.
So I will open the camera. I will open my.
I've been stopping
Yes,
sharing
present. Yes,
basically.
yes, 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 yes. And let us show the uh, comments anyway. So one person at the very beginning wrote that liked it, and the person Sunil Chaube, uh, he's doing some postdoctoral research probably in some which country I just saw now. So he's looking forward to the next two episodes. Asks that when it will be, and next one professor from Cochin University of Science and Technology. Uh, while we are trying to share the screen, he actually tried to help us with some comments. These are the reactions generally come on LinkedIn. Of course, there are really interested people who study. So when it is recorded, and it will also be seen later by others here on LinkedIn and also on YouTube. And since we have scheduled this episode only yesterday, 24 hours ago, that is also another reason many people probably could not get the intimation. So, in the next episode, when the part two will be streamed, and in the meantime, some other people also will get to know about this mini workshop on computational photonics. Uh, more people will, not only they will join, they will also see the part one recorded videos. So uh, that way it started quickly. I mean, you can say that as it is started only 1 week ago. So uh, you can give your comments about how you will present in the next part 2 and part 3, because there will be interest from some audiences, serious audiences, some research students, master students, and some postdoctoral researchers, because this is a subject which is very deep and very few will study. Okay, what to Professor Cole, if you please.
Yes, okay. Yeah, are we on? Okay, yes. Can you hear me?
I can hear you. Yes, you can lower the
Yeah,
sound of
I
the
think
speaker.
now we have
Yes,
good sound. Yeah.
yes, nice sound. Yes,
Oh, I
please.
can't hear you. Oh, wait a minute.
You
Maybe I'm
cannot hear me?
muted. Wait a minute. I can't hear.
Uh,
Uh, so, Bosh. Yeah. Wait a minute. I think we're somehow.
You were fine.
Am I fine? But I don't hear any sound.
Saswatee, can you hear me?
He's
No.
talking and I don't hear anything.
Then this thing has to be. No.
All right, now can we hear each other?
Yes, 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 yes. Can you hear
All
me?
right, now we're fine.
Yes,
Yes, now I can hear you. Yes,
yes,
now
please,
it's fine.
please. Please give your, I mean,
All right, so
what I told that about the next episode and the part two, part three, and because it is a deep subject, not many people like to enter into Maxwell's equations. So, what is your advice and how we do appeal to the learners, even say at my age also? I remember in 2009 when you visited Kolkata, that Icon Top conference. So I asked you where to start. So so you can actually give some clue so that the next episodes people will get some clue how to start with computational photonics and that approximation of that Maxwell's equations solutions.
all right, so let me just comment that first of all, there are many, as I think Dr. Banerjee explained, there are many methodologies, there are many software packages to solve Maxwell's equations. But to really understand what you are getting out of these packages, what you are getting out of these solution methods, you do have to understand where they come from. And you may not be an expert in the calculations, but you should understand the theory behind them, because if you don't, you will not really be able to interpret the results. And let me give you an example of just where this understanding is necessary. Some years ago, I was cooperating with someone this was in Japan, and a student was interested in synthetic aperture radar to image the ground below. Now, perhaps synthetic aperture radar is a way of taking many radar images and then combining them together to get very high resolution. Okay, so this student was using FDTD, the finite difference time domain, to make some calculations. And whenever I see someone using the finite difference time domain method, I always ask, well, we haven't explained what FDTD is, but what it really is you take the equations and you put them on a numerical grid. So the x-axis is discretized. So instead of an analog system, you have 1 delta x, 2 delta x, 3 delta x, 4, the z-axis, and then time is also discretized. So that time step and the space step is very important to know. And then if you know the wave, you must know the ratio of the space step to the wavelength. You must know the ratio of the time step to the wave period. So anyway, I asked this student, what is your wavelength? What is the ratio of your wavelength to the space step? He didn't know. So we figured it out. He gave me some information. We figured it out. And it turned out that there were only 2 space steps for each wavelength. Now, perhaps you know that a wave oscillates. It goes in a sine. And if you look at 3 points on that wave, the beginning, the middle, and the end will be 0. So if you're, depending on what the phase is on this interval, you will see either nothing, or you will see a signal that very imperfectly represents that signal. This is actually elementary signal theory, not necessarily Maxwell's equations. So it turned out the results he was getting were nonsense. And then some years later, after this, I was collaborating. I was still in Japan, but someone wanted to parallelize one of my algorithms on a supercomputer at the California Institute of Technology. So this is a very powerful machine, or was, and I mean, it was one of the most powerful in the world in those days. I'm sure there are many more powerful ones now. But anyway, so this expert was working on this, and this fellow understood computer science very well. He understood high performance computing very well, but he didn't understand the basic science. So again, he was using 2 grid points or 2 grid intervals per wavelength, and nothing was working. It was just the algorithm was unstable, meaning that you calculated and it would go to infinity. You would get nothing. And again, I had to advise that no, you cannot do it this way. So this is where just knowing, you need to know the basic science. And I would advise any student in computer science, don't just study the computer science, study what you're going to apply it to. So if you're going to apply it to optics, you'd better learn some of the basic optics, some of the basic physics behind it. And also you should learn some of the mathematics, because when I started, I liked mathematics as insofar as I could use it. But then one day, when I was actually someone from India was visiting, I think from Hyderabad, I forget the name of this, Dutta Gupta, I think it was his name.
Okay.
Yes.
Yes.
He was visiting Tsukuba, Japan, and I was showing him my algorithms, and he asked, can it handle resonances, me resonances? So this is again a resonator where the wavelength of the structure, the size of the structure and the wavelength are very similar. And I said, oh, of course it could. Well, I tried it out and it didn't work. And I was really worried because I had published papers on this and it was not giving the right answer. And then finally, one day, so I gave this problem to a student and I was working on it myself. I was desperately trying to find out where an error could be. And I couldn't find it in the algorithm. And so I thought, well, maybe the analytic method that I use to compute this, because they're with a single cylinder or a single sphere, you can get an analytic solution. And I was comparing analytic with the computation. And I looked very carefully. Maybe I made some mistake. Maybe, of course, the analytic solution, as you saw in one of my slides, is an infinite series of Bessel functions, either cylindrical Bessel functions or spherical Bessel functions. So I thought, well, maybe I'm not computing them correctly. Maybe the package I'm using is not computing them correctly. So I went back to the basics and started computing them myself. Still, nothing worked. Then this is where sometimes people who don't know everything, or you think you know everything, but you give the problem to someone who doesn't know everything, and they're an amateur. So this student ran the program for a few 100,000 time steps. Now, in all the previous runs, a few thousand would do it. Even a few hundred would give you the right solution. But he didn't know that. So he went through 200,000 time steps, and we realized that the analytic method and the FDTD were agreeing. Well, why did it take 200,000 time steps? Well, this is a resonator. Light is trapped in the resonator. We were putting light in from the outside, and so if it comes out slowly, it's going to go in slowly. So it takes a long time to see the right solution, the light coming out in the right way.
Yes.
If you would put the source of light inside the resonator, you will see the solution quite quickly. And so I could say that I'm ashamed of myself that I should have known this, But I did not know this because I hadn't thought about resonators. So the moral of the story is you should really, before you try to compute anything, before you try to simulate something, you should have an idea of what the science behind it is. And without that, you will not be able to. You need an intuitive feeling. And this great physicist, I guess the greatest one of, well, there were many great scientists in the 20th century, so never say greatest, but one of the very great scientists, physicists of the 20th century was Richard Feynman. And he always said that he would guess the solution first. Well, it may not be a good guess, but he would guess it first and then try to analyze the problem. And with a good guess, you can get very close to the correct solution. And so I a little bit in some of my work when I was developing algorithms, at first I tried to guess a solution and it didn't work very well. And then I started doing numerical experiments. And then I found something that seemed to work. And then I went back to the mathematics and proved that it worked. So you can start with a crude understanding, a very crude model, and then you refine it slowly. And I think humans have been doing this. I like history, so since the Stone Age, we started out. If you go to the museum, you will see some very simple stone tools, and then the next person came along and made something a little bit more sophisticated, and then finally you get a very beautiful tool, and then on it goes, and then metals came along, and then all our technologies, and then very rapidly we advanced. So this is the way you have to start, and you yourself will develop your skills by starting with the basics, however imperfect your understanding might be. And don't try to understand all the details from the very beginning, because gradually they will grow upon you and you will appreciate them. So this is my advice to anyone, whether you're a beginning student or a mature researcher, that you can start out with an imperfect understanding and then gradually refine it step by step.
Excellent. And it is the best answer I got, like the experience based guess and intuition. And that is the best thing, best tool, mental tool we have. Okay. Thank you very much for clarifying it, and giving the insight to whoever is willing to study, say, FDTD method and or any other methods or any other subject basics. So
So in the subsequent podcasts, what both of us will do, we will now go into some of the details. We will avoid overwhelming you with too many details, but we will start step by step and show you how you model these things and give some simple examples, and then give a flavor how to do more complicated problems.
so perfect. So uh, Saswatee, if you also say about the
Mute my
next
microphone.
episodes, can you hear me? Yes.
Yes, I can
Yes,
hear.
I muted the microphone. Yeah.
Audio.
Oh, I'm not muted for some reason. Why?
Okay, now it's good. Oh,
Is it
the
okay?
speaker, the speaker. Switch off the speaker.
He did.
Here, why don't you talk into this thing? This, this key doesn't seem to work. I mean, this button here. Now try. I think I'm.
Yeah. Okay. Okay. Now it is mute. It is not, microphone is not on.
Yes. Can you
Yes,
hear me?
yes, yes.
Oh, so, okay. So, uh, uh, what as I mean, he said. In fact, I will build up on that. That is, I mean, it's not something that you can learn in one day. And I mean, you really fail a lot, and you go through the hard work. Then you slowly learn, and also it's not totally unsupervised learning. Yes, it's pretty difficult, and you work with other people, you work with more professionals, and it's a collective understanding. You slowly grow your understanding and you learn this. However, I would suggest one thing, that there is I noticed among a lot of people there is a feeling that there are commercial packages and you just click on it and it will work, but it doesn't. Basically, just clicking on it doesn't work. You do have to learn the nitty gritties of these things, and also the commercial packages don't solve all your customized problems. So you might have some problem where, I mean, for example, yesterday we were discussing some problem where it's not that there's no solution, and it's not like people didn't try, but people tried. There are solutions, but the problem is each result is different. Apparently that they cannot get a convergent result. So that is so it can happen. There are plenty of places where you might not get a very accurate result always. So it is important to understand the physics, the actually in fact there are, I mean, I did not show it here, but in fact what I did many times, there are effective theories. It doesn't have to be perfect, I mean, rigorous theory. Sometimes you can do zero order two theories, effective theories, and then you can have a guess what it might come to, what you might be able to see in this thing. And this is where some of those analytical methods, analytical solutions come into effect. For example, if you can show that, okay, this is my model works with a standard problem, then that particular model, you take it and try to solve another problem, then you are more likely to have a better answer and understanding, basically. So I think, yeah, there are it's always very important. We always did, we compared our results with, say, for example, me scattering results. I mean, if it is not working, I mean, also, there is this Born and Wolf has this characteristic matrix. I implemented that, I compared constantly with FGD results, etc. This is just to make sure that what we are doing with the numerical method is actually agreeing with the analytical solution. And also another thing is, of course, the fabrication, the actual sample, analysis of the actual sample, the measurements. That's the way to go forward. But you still have to go back and forth, because both the fabrication method has to be refined and your simulations have to be refined. So it fits back into each other, basically. So yeah, it's not a simple answer, but you have to slowly you develop your understanding of the system, I would say.
Okay, thank you. So you have concluded rightly what Professor Cole started. So the basic understanding is a must. If it is not done correctly, then a software or even a supercomputer cannot do the job. So uh, for the next episode, that part two, uh, we can schedule this uh, more quickly than this one, because we know that we will do it. So we'll schedule it on maybe uh, Wednesday, so there will be enough time to people get intimation. And after this episode, some people will get to know that this mini online workshop is going on in computational photonics, and we will have more attendees. I mean, although many people clicked in LinkedIn, it happens. Many people click to join, and then either they forget, or they are not very seriously interested to go through the detail of the presentations or discussions. So anyway, it is recorded, and we will also um, check ourselves later, and we will refine it in the planning and execution from the next part 2 and part 3. So if Professor Cole also comes to the screen, so that we can say yes.
Yes, I
So
will on my.
yes, any
Yeah,
final word, or then we can.
I should turn on the video. Yes.
Yes, yes,
Okay. Now
yes,
I am on the screen. Yes.
yes. So
Yes.
any final word, then we can stop the streaming for today and look forward to the next 2 episodes.
Yes, so I'll look forward to meeting everyone the next time, and we'll go into a few more details. And as Professor Debesh has said, we will uh, be a little bit more brief. We had some technical difficulties today, but I think we've overcome these and learned how to control them next time. And then we will go into some more details. I think we've given you a flavor today, but we'll go into some of the more details and show some demonstrations that we hope will convey the intuition as well as the mathematics of these equations that we're talking about. So thank you
Okay,
very much.
okay. With that, shall we end the stream now?
Yes, I think we're ready. Yes,
Yes,
I think
yes,
it's getting
yes,
late
I think
for everyone.
thank you
yes.
very much for everybody.
Okay, we'll see in the next episode, coming Saturday, December 13th. Okay,
Okay.
okay.
So good night.
Say
It's
good,
nighttime
goodbye, good
there.
day,
It's
good day.
our
Okay,
afternoon here. So good night, everyone.
okay.
Bye bye.
Bye bye.
Bye bye.